I'll tell you the truth, I haven't really thought about the nucleus of an atom, how it works, because, I got to figure out a hydrogen first, and before that I got to figure out the electron spin. But I did want to say, hydrogen has two, this is rare over here to have a neutron with it. Usually it's just by itself, right? Now if they're spinning, remember at the first part one, right? We showed that if they had a perpendicular spin, that they would lock in and be stuck together, a certain length apart, right? So let's say we did that, and this electron's orbiting, right? It's locked into position, and it has, as it's being swung around here, gravity is pulling down space-time so that it doesn't feel any acceleration due to the orbiting, okay? I'm not convinced that just because an electron accelerates, it shoots off photons. I mean, yes, if you accelerate it by changing its velocity by speed, yeah, definitely. 100% shooting off photons or whatever. But if you just accelerate it and then it has a constant speed and it's just orbiting, I don't think, because it's constantly spinning and it isn't giving off photons, I don't think acceleration due to change of direction, I don't think that makes them shoot off photons. But who knows? We'll see. We'll know sooner or later. So how are these, right here. Remember I said neutrons are little tiny magnets with zero charge. So they can have perpendicular spins, right? Have that magnetic lock, right? And that's how it's done. Or they line up with their spins the same way, just like if you have two magnets. You put the south to the north and the north to the south, and they attract each other. That would do that to there, and they would be snapped together, you know what I mean? It's one or the other, I don't know. Look at helium, right? This is rare to have one neutron, right? But if it does, it's either like this configuration, where they link up like three magnets, right? Because the neutron doesn't have any charge, right? It keeps the positives far enough away so that their charge isn't repelling, but they are magnetically locked together. Or they have their spins different, right? Perpendicular, so that they get locked in where they're at, right? That's with helium with one neutron. What if it had two neutrons? You can either link up like this, or again, they just have opposite spins, perpendicular spins going around here, and that locks them all in, right? Or again, it could be this. Now if we go with this motif and we go to lithium, right, that has three protons, it'd be like this, or maybe like this. But I don't think, you can't do that forever. You can't line up your, you know what I mean? So probably more like this, where they're bunched together kind of, see, and they're separated by the neutrons, but they all have different spins, so this spin right here is the same exact, you know what I mean, to lock them all in together so that they can't escape. Here's beryllium-4. Again, we want this motif here. You'd have to have that. Again, seems unrealistic, at least once you get up to here and here. So it might be something like this. Got your, the neutrons in the side, separating the positives, and they all have different spins so that they lock each other in. And the last one we're going to say is boron, which has 5 and 6. Probably is set up like this, right? Same way as this over here, right? The only difference is if you turn this over, like, right now it's like this. If we did it like that, so this was that whole thing, and then put a neutral on this and then another positive, and then on the other side of the board you put a neutral and a positive, so it looked like that. I don't know, these are I just basically thought of these literally right before I did the video, because I haven't really thought about the nucleus. Because like I said, the first step is mastering the hydrogen, right? And even before that is mastering the electron and how it spins, how it orbits, and all these different fields, how they all interact with each other, right? This is my proton. I drew because it's spinning, right? And I drew the flux line, same with the electrons, right? And I've drawn 100 pictures of this, different orientations, different places, all over the place. I just drew 2 on there so you can see. All right. Now the electrons, right? If I could, that circle there is like this. If I could pick it up like that, right, from front to back, you would see it's going counterclockwise. Same way with this one. If I could flip it up, you could see that it's going counterclockwise, right? So that means that this would be south and that would be south. The proton, if I could take this and this circle here and go up so you can see it better, it would look like clockwise. It would look like just like a clock. So this proton is spinning different than these two. So why are they all blue on top? Because when you spin a proton, the north and the south are opposite from what an electron does when he spins, right? There's no spinning clockwise and counterclockwise. If anything spins, they spin both ways. All you have to do is walk 180, turn it around 180 degrees. Anything spinning clockwise, turn it 180 degrees, it's now spinning counterclockwise. So you can't say a proton spins, this way and an electron spins this way. Because that's stupid. They spin both ways. Right? But the magnetic pole is put on an opposite side, right? So now they have their poles the same, right? But they're spinning different. So I've been thinking about this over here is how do you put on a proton, right? How do you put the electrons on, right? You know what I mean? You put it on here like that, you can see that the flux lines come out and they're matching up with those flux lines. Or maybe you put them in between the flux, because look, this is coming out of this little electron and going up. Same here, this is going up. It's coming out and up, up. They're both coming up. So maybe you can lock it in there. Maybe you can, these flux lines or levels, energy levels, that you can jump from one to the next. Or, okay, this needs to be turned 90 degrees maybe. It's like we said, if you have your magnetic dipole perpendicular to this guy and you're spinning, you'll get locked in, you know what I mean? Maybe this is turned this way and locked into this orbital. Or maybe it's down here. You know what I mean? Keep in mind, I saw this video after I did the last, the first 7 minutes of this video. Then I found this and put it on, so this is making me even think, this guy's going to do all the work for me, man. This channel is called Magnetism DTU. The video is called Magnetic Levitation by Rotation.
Thank you, and you may get started.
Okay, hi. Can you hear us properly?
Yes, we can.
Okay,
I'll give an introduction very briefly. Your talk is entitled Magnetic Levitation by Rotation, and will actually be given by the two of you, so this looks very exciting. Thank you so much.
Yeah. Hi, I'm Joachim, and this is Karek, and we want to talk about recent work on this newly discovered type of magnetic levitation. And our work, we've already gotten it accepted in Physical Review Applied, and we expect the paper to come out within the next few days. So, first of all, the phenomena is quite simple to create. All you need is two magnets, one that you spin very rapidly, and once you approach that rotating magnet near a free magnet, you will see that the free magnet locks on to a specific point and will levitate as you move it around. We've then investigated this more thoroughly with a setup with better quantity control and better speed control. And here we see that the rotor magnet is attached to the motor with the north and south perpendicular to the rotation axis.
That's important. One of the magnets have to be not spinning the way you'd think, with the axis of rotation being like the actual north and south. One of them, see how this top one isn't, it's going to be rotating, it's not going to be rotating the way you'd think. They have to be perpendicular.
And when you then place a floater magnet or free magnet underneath, it will find its equilibrium quite quickly. Here in the video, you also see this aluminum plate we have underneath, and this is to create eddy current damping in the free magnet that causes the oscillations to stabilize and thereby making the initial conditions more consistent. Using these experiments, here we have painted the north poles of both the rotor and the floater magnet. We see that the floater magnet orientates almost vertically, processing.
See how it's gonna. Here, well, I'll start it with no thing. Look how it wobbles. Do you see that?
Mixed with the rotor magnet. We've then also floater magnet orientates almost vertically, processing synchronized with the rotor magnet. We've then also done some simulations. For this one, we started from rest, and here it finds its equilibrium point quite quickly and processes in the same way that our experiments show. Now to the modeling.
Yes, so for the next part of the talk, we will try to explain why this phenomenon occurs, why this levitating state of this exotic moment configuration is stable. So in our model, we have a dipole magnetic field from the rotor acting on the floater. We have drag, which we model as proportional to the linear and angular velocity. And then we have gravity. And because the dipole field decreases with distance, it has gradient, so it produces both a force and a torque that tries to align the floater moment with the dipole field. Putting these into Newton's second law for translation and rotation, we get these equations that we can time step integrate to get the full time evolution, as you saw in the last video. And it turns out that it is extremely important that the rotor magnet is somewhat shifted relative to its rotation axis or has its moment tilted. Because then, besides a rotating horizontal field, there is a vertical static component of the dipole field and the floater. And only then do we get this counterintuitive configuration with the moments north-north and the floater almost vertical with some angle theta. Now I will go through the torque and force balance in steady state. So it seems at first that this dipole torque is unbalanced, so the moment should flip over. But it is in fact counteracted by the rotation itself. In our simulations, we get this state of rotation where the floater moment precesses at the same frequency that the rotor is rotating, moving the arm, but it has a second rotational mode around the moment itself. This is analogous to a spinning top, where you also have spinning around one axis and precession of that rotation axis around vertical. And just like the spinning top can stay upright against gravity, the rotation allows the floater to resist this magnetostatic torque. In fact, when we analyze the system in the rest frame of the rotor, then the magnetic field and the dipole torque are constant, but we get this fictional gyroscopic torque from the rotation and inertia of the floater. So that's the explains the orientation of the moments. To explain the levitation itself, we need an attractive force and a repulsive force. The attraction comes from the vertical components of the dipole field and the floater moment, while the repulsion comes from the horizontal component, because the horizontal components are anti-parallel and so lead to repulsion instead of attraction. There also is the effect of gravity, but this is a small and unnecessary correction. The phenomenon is fundamentally magnetic.
See, that's what I'm saying. I'm saying the magnets are going to lock, if you have electrons, right, they're going to get locked in by this this magnetic thing here, where this locking mechanism. And then they're going around, but gravity is pulling down space-time, right? And as long as that electrons are going around at the right rate, they will never feel any acceleration from change